So lecture 2, maybe we start with a reminder. So let's remember our favorite thing from the last lecture. Okay, there's no doubt what I'm talking about. It's this guy. Yes. All right. So we decorated the target of the Frobenius map, orange R. Thank you very much. Yes. Okay. Right. So this was just a decoration to illustrate or to orient us as to who we're thinking of as the source of Frobenius versus who we're thinking of as the target of Frobenius. And the reason that we did this was because sometimes we wanted to compare things on different sides of the Frobenius map, the source and the target. In particular, right, this decoration is telling us maybe that we should be thinking about, when I write this, I'm thinking about R as an R module by restriction of scalars through the Frobenius map, which explicitly means that R times orange S is orange R to the P to the E times S. Okay. All right. So this was our reminder about our favorite thing from last time. Okay. This has nothing to do with Frobenius. Let K be a field and R be a polynomial ring. Oh, S, I guess, was our name for polynomial rings. Polynomial ring in one variable. See, yeah, I think I can do this in one line. Given any two polynomials, their product is in the ideal generated by their squares. Maybe you're saying, oh, there's Frobenius. Well, I didn't say it. I mean, characteristic is nothing to do with any of the characteristic. Okay. And this isn't so hard to see, but let's do it just because it really has nothing to do with Frobenius. Okay, give me a name for the GCD. I am in a PID. Right, I can get back to the GCD. Oops, that's not what I want. Okay. I don't mean derivative. I just mean whatever's left. Right, factor out the GCD from these things. Right, and because this, well, I was calling for my GCD in terms of this, ideal notation, using the fact that I'm PID, I can get from F and G back to D, or I can get from F prime and G prime back to 1. These are now coprime. Euclidean algorithm, whatever. All right, that's nice. So what? Then plug in everything. D F prime, D G prime. There's also an invisible copy of 1, I guess. So let's plug that in. And let us gather. One of these terms has 2 F primes and some other stuff. And another term has 2 G primes. And and some other stuff. Two. Yeah, I explicitly exhibit it as a combination of S squared and G squared. All right. Polynomial ring in two variables. What do we think? Can I do the same proof? No, definitely not a PID. Do we think the statement's true? No. Do we see any polynomials? Yeah, or even better, right? If there's like two interesting or not interesting polynomials in this ring, how about X and Y? Okay. Okay, well, this was probably the wrong thing to ask for. Probably I needed to, take three things, right, to get, bigger than the number of variables or something. And you can try a number of triples of polynomials, and you will often see examples where f times g times h is in f squared, g squared, h squared. Onrog showed me one where it wasn't. Onrog C. So. You can check this. I think you have the tools to check this. It's too bad. Oh, I should probably save this. Yes. Oh, yes. G. Which G? Oh, yep. Yes. Yes. Thank you. Good. Good. Okay. We remember this one. But the next best thing is true. Maybe I'll circle back to this. The name. Emphasize any. Bump everything up by one. Same thing with polynomials and variables. Okay. So our goal is to prove this at least in a reasonably general case. So take a ring of characteristic P. And an ideal in that ring. I'm going to define two variations on the ideal I. The first says that I want to take an element and ask whether it is asymptotically an I with respect to Frobenius in this sense. Large Frobenius powers of my element, Frobenius images of my element, are in the corresponding large Frobenius powers of my ideal. And the second is like this with a small nudge. This is what's called the tight closure of an ideal. And the definition certainly deserves an attribution due to Hogstrom-Hemke. Yeah. Oh, yeah. Oh, sure do. Yeah, thanks. Or, good. Okay, you're going to replace the worst part of this definition with C is non-zero if R is a domain. Okay. And we'll be interested in some domains at some point. Might have one more line left to sneak another node in. If I am in I, then my p to the eth power is definitely in the ideal generated by p to the eth powers of things in I. I'm a generator of that ideal. And if I'm in here, I can take C equals 1. I didn't even really need a nudge. These containments are always true. And the theorem that I want to talk about, the positive characteristic theorem I want to talk about. May sound a little bit boring, but then we'll realize actually that it's exciting. over a polynomial ring, or more generally a regular ring, we get nothing new. Okay? So why does this look boring? I made up this weird notation for something that wasn't different. Why is this exciting? It means that if I want to test if something's in an ideal, I get to cheat, right? I get to, move some stuff around and really test things that look a priori weaker than f is an I. Let me mostly prove this. I'll leave out some of the details. We've already done the most important detail, though. So let's make this a section instead of like proof environment. So let me recall a piece of notation. Or a ring, element, an ideal. This colon construction asks for the elements that multiply me into an ideal. Just a convenient bit of shorthand. Let me also, oh yes, please. Capital A. Oh yeah. Let me avail myself of a fact. If I have a ring homomorphism, oh, sorry, let me continue with my hypothesis. Such that B is a flat A module by restriction of scalars. It's the only way to judge B as an A module, given if we only know what's on the board. Then this colon business plays nicely with whatever we've written down here. I can compare J and A in B by sending A to B directly and by making the ideal that we make out of J in B. I could also not, and then make an ideal in B. This fact is not so hard. Of course, we have to know what a flat module is. If you don't, then you're encouraged to try to prove this for a free module, since we know two things about flat modules in this lecture series. One is that free modules are flat. What's the other thing we know? Kuhn's theorem. Interesting. All right, so back to the proof. There's only one interesting containment to earn. Given element in this bigger thing, we need to show it actually was in I. So what's it mean that A is in I star? Okay, I said a polynomial ring over a field, so you just say I have a domain. Okay, so. Definition, good. All right, now should probably try out this cone notation, yeah? Okay, I know I want to be working in the context of Kunz's theorem to apply this. So I'm going to turn this orange, okay, and then I'm going to be ready to recognize that Kunz's theorem is relevant. Oh, all right, yes, let's do that. Yes, the parentheses match. All I've done is rewritten this in orange. Okay. I can do interesting things to both sides of this equation. I can apply exercise 5 to this. Okay. And less exciting, I realize that this is the result of applying the Frobenius map to A, the E Frobenius map. Okay. I have one of these things. Okay. The hypotheses of Kunz's theorem apply, or it means that the lemma fact applies. All right, that's a fact. Okay. You can move the target ring out. This. And now I'm going to apply the exercise again. Nope. Whatever this is, it's just an ideal with a funny name. Yeah. Okay. All right, I've had enough of this orange. Frobenius powers are contained in powers. Another fact from commutative algebra. The intersection, we're in a situation where the intersection of all these powers are 0. Okay, so C is 0. And we're done. Yeah. No, that's not true. Let's redo this. When is this 0? It's a proper ideal. This happens whenever A is not an I. Okay. 1 multiplies A and I otherwise. Okay. Okay. This would lead to a contradiction. Okay. The only option was that we start out with something like that. Okay. So a little bit of monkeying around to be done. The thing we want to note is that Kuhn's theorem was what made this work. Good. All right. No, I gave it a name, but I erased it, huh? Oh well. We can rewrite it. So I'm going to apply this fact to prove theorem A. I'm going to give myself some extra hypotheses just for convenience, not because they're really necessary. But I didn't give myself as many of these in the notes, so you're invited to check those out. And maybe I'll just stick with the FGH. The same proof works the same, but I don't like subscripts that much. And just to make my life easy, I'm going to assume FGH are homogeneous of the same degree. And if you're worried that, oh, wait, did this make this trivial? No, the example that showed this was sharp was for things that were homogeneous of the same degree. So maybe this is the most exciting case, actually. Okay, so. I do need one other fact from commutative algebra. It's not trivial, but it's a relatively standard sort of thing. And I'm only making these unnecessary assumptions that I'm homogeneous of the same degree and infinite to make this lemma work without having to say, reduce the local case or whatever. sorry. Actually, I apologize. I'm going to give myself some subscripts now. We'll go back to FGH when we're into the good stuff. If a power of an element isn't a power of an ideal, same power. Then with a little nudge, with a little nudge, large powers of my element or large powers of the ideal generated by two general linear combinations of my generators. This follows from some standard things in integral closure, and there will be an outline of how to prove this in the special case in the Thursday homework problem set. If you're curious, please, yeah. And yeah, so if there's more variables, okay. Yeah. Perfect. Yeah. Just increase corresponding number of linear forms. Yeah. All right. Okay. I erased the statement, so let's remember what we're trying to do. We want to show that the product of the squares is contained in the ideal of the cubes. Okay, so now you'll see why I called those FGH and then uncalled them, recalled the letters FG and H. F cubed times G cubed times H cubed is a product of three things in the ideal generated by F cubed, G cubed, and H cubed. Good. You are here. And now you're here. Let's see, GH. So T. that gets us large powers of FGH contained in the ideal generated by general linear combinations of F cubed, G cubed, and H cubed. I know a large number, p to the e, even 2 times p to the e, yeah. Even larger. All right, what happens? All right. This is just an ordinary power. I can write generators for this power ideal as monomials in the L's, right? Every one of these is at least p to the e. Some sort of pigeonhole principle thing got applied here. Good. Oh, you can't use orange. That has a very specific meaning. Let us think of this like so. This is C times something raised to the p to the e. This is the definition of tight closure. Oh, all right. Something exciting happened here. Okay, L1, L2, they're just linear combinations of F cubed, G cubed, and H cubed. Oh, yes, that's what I'm going to show. Okay. This is a completely typical application of tight closure. One can show containments that are not at all obvious by boiling things down to the pigeonhole principle and the fact that we're allowed to cheat, so you get a little bit more room here. This is actually secretly a proof of a statement about integral closure, Branson's Coda theorem. Good. Yes, that's all I wanted to say.